Hi class. So in this video, we're going to continue our discussion with chemical bonding, but focus on covalent bonding. So rather than ionic bonding, where there's a complete electron transfer, we're going to focus on covalent bonding, which requires a sharing of electrons. So with covalent bonds, we have nonmetals bonding with other nonmetals. Electrons are shared in a covalent bond in order to achieve an octet. The potential energy is lowest when the electrons are between the two atoms sharing these electrons. So this picture depicts exactly the electron being between the two nuclei of the atom is going to create the lowest potential energy level or the most stable situation. So shared electrons hold the atoms together because it attracts both of these nuclei. Electrons that appear in the space between atoms count towards the octet for both atoms. So whenever you have shared electrons between atoms, those are going to count towards both of their octets. So let's talk about satisfying octets and duets. Why is it H2O? Why is it not H3O, H4O? Why H2O? So we learned earlier with bonding patterns, hydrogen has one valence electron, but it wants to be like helium, which has two valence electrons. So it wants two. How can it accomplish this? By forming one bond. Oxygen has 6 valence electrons because it's in group 6A. Two pairs are already paired up, but it needs 2 more electrons because it has 2 unpaired of the 6 valence electrons. So it likes to have an octet, so it needs 2 more, and that creates 2 bonds and 2 lone pairs. So how could this happen? Well, we know that the oxygen has 6 valence electrons, but wants 8. Each hydrogen has 1 valence electron, but it wants 2. As these valence electrons, or as these atoms approach each other, the valence electrons in their outer orbitals begin to overlap. As they approach, the overlap results in a sharing of electrons. So now hydrogen shares one, oxygen shares one. We see that in this bond. The hydrogen valence electron here and the valence electron of this oxygen, now that space overlaps, and we see that here. So again, the electrons between atoms count towards both of the nuclei. So we see that oxygen actually has a duet or an octet. Why? It has 1, 2, and then we count both of these in the sharing, 3, 4, 5, 6, and then both of these in the sharing, 7, 8. It has an octet. The hydrogen has a duet. How did this happen? Hydrogen formed 1 bond, and the oxygen had 2 bonds. But what's the difference between a shared pair and an unshared pair? So electrons that are shared between atoms are what we call bonding pairs. So the bonding pairs are shared in between the atoms. The electrons that are not in between atoms, that are not shared, are called lone pairs. They do not overlap in the region of space with the other atom's outer shell. So in that last slide, we saw that depicted as the lone pairs not being between the hydrogen and the oxygen nuclei, but only by the oxygen. So one of the key things is when you're showing bonds or shared pairs, we're actually showing them as lines. We know that 1 dot came from the hydrogen and 1 dot or 1 electron came from the oxygen in both of these bonds. We understand that. but we're showing because they're shared and there's an overlap between the two atoms, we're depicting them as lines. So bonds or shared pairs are lines. Lone pairs or unshared pairs, so these are not used for bonding, these are unshared, these are represented as a pair of dots. When we understand the basic concepts to Lewis dot symbols, it really helps us understand diatomics. So again, hydrogen, they each have one valence electron. What do? As they overlap and approach, there's two electrons between the two nuclei, and we draw one bond, one line. Chlorines, we know that each chlorine is group 7A. It has 7 valence electrons. As these approach each other, the two unpaired electrons overlap in the same region of space. We see that there's only 2 electrons that are being shared between the two atoms. So how do we show that? We show that as a bond, which equals a line. The other electron pairs are not shared between the atoms, and we leave them as what are called lone pairs. But sometimes we have to share more than just 2 electrons to satisfy an octet. Those are referred to as higher order bonds. You're probably already familiar. These are our double and triple bonds. So double bonds is when I need 4 electrons to be shared. So we see that with oxygen, the diatomic O2. Each oxygen has 6 valence electrons, right? So we see 6 here and 6 here for a total of 12. But if we only had these two in between, this oxygen on the left would not have an octet. So one of these lone pairs is actually not a lone pair, it's also shared. So we see a sharing of 4 electrons. Now both oxygens have an octet. 2, 4, 6, 8, and then we can see on this side 2, 4, and again 6, 8 for the ones in between being shared. So how do we depict the 4 electrons being shared? Each line represents 2 shared electrons, so we show 2 lines, which is a double bond. Can we do the same to represent triple bonds? Of course. Triple bonds are when you share 6 electrons. We see this in the case of nitrogen. So nitrogen, to achieve an octet, has to share 6 electrons. And that's where we get 3 lines to represent a triple bond. And if you remember from the earlier video, oxygen's bonding pattern, right? It has 6 valence electrons. It likes 2 bonds and 2 lone pairs, like we saw with H2O. But you can get 2 bonds by having 1 double or 2 single in the case of H2O. In nitrogen, we showed that it has 5 valence electrons, so it likes 3 bonds and 1 lone pair. But the 3 bonds don't have to be single bonds, like in the case of ammonia. You could have 1 triple, like in the diatomic of nitrogen, or you could even have a double and a single. As in the case right here. One of the things you should know about single, double, and triple bonds is the more electrons shared means the closer the two atoms will be. So the internuclear distance, you can think of that as the length of the bond shortens as I have more shared electrons. PM stands for picometers. And we see that a single bond, and this would be, a single bond probably for the same two. I believe this is for single bond of carbon. This would be a double bond, and this would be a triple bond. But what we see is as we share more pairs of electrons, the bond gets smaller. It also gets stronger. It's harder to break. I always tell students a good way of thinking about this is if you share with your partner more, you're closer and it's harder to break you up. If you share less, it's easier to wedge in there and separate you and break you apart. I hope this video helps you understand Lewis dot symbols and how they're incorporated in covalent bonding, and also the discussion, the little analogy for single, double, triple bonds, their length and strength. Thanks for tuning in.